Misty, and I want to thank you for joining me today for a MeWe. I'm glad you asked. A MeWe is a meaningful watershed educational experience. We offer this sort of hands-on educational experience because water shapes our past, our present, and our future.
So, what is a watershed? Because we all live in one. The simplest answer is that it's a drainage basin, an area of land that contains creeks, streams, or rivers that drain into larger bodies of water. Here at the museum, our local creek is a part of the much larger Chesapeake Bay watershed. The Chesapeake Bay watershed is the largest estuary in North America. It has 64,000 miles of shoreline, stretches across 6 states, and is home to over 18 million people. The human activities in that watershed affect the ecology of the entire estuary.
To understand those effects, we start with our 3D model to show the two types of water pollution, point source pollution and non-point source pollution. Point source pollution is easy to remember and easy to recognize in your community because you can literally point right at it. Our industrial plant here, our sewage treatment plant, and this stormwater drain are excellent examples because you can literally point to where they enter the water body. But you can see many other areas on the model where stormwater movement might pick up pollution and carry it to the water body. For instance, if oil or gas from any of these vehicles leaks onto the ground, it will make its way into the water body. If the soil in this construction site is not contained, it will make its way to the water body. And if there's excess fertilizer and pesticides used in this neighborhood or on this farm, it will make its way to the water body. It is much more difficult in these cases to point to just one source of pollution. So now that we've identified our potential sources of pollution, let's see what happens to this watershed when water moves across it. We're going to make it rain. We even sometimes have flash floods. And as you can see, several of these different types of pollutants have ultimately entered our water body. So, what can we do to help fix this situation? For some of our runoff, we can plant riparian buffers, which is literally a planting buffer next to a water body. We can also plant trees to help prevent erosion. On our construction sites, we can put up silt fencing to prevent erosion. And on our farms, we can do contour plowing to help prevent erosion. Now, to keep our friends from doing what they do in the creek, we can fence them in. We'll have to provide them with a source of water, but they won't be over polluting the water body. And with fertilizers, we can do our fertilizing at different times of the year to help reduce nutrient pollution in our water body.
Most water bodies are not actively monitored, and this is where citizen scientists can be most helpful. The first type of monitoring conducted is a series of physical and chemical tests. These tests give us insight into current stream water conditions, or a snapshot of the state of the stream, if you will. These tests can detect introduced pollutants like fertilizers and determine the natural constituents of the stream like oxygen level or alkalinity. Let's look at our common tests. First, we measure the turbidity of the water. This is a measure of water clarity as it indicates the level of suspended solids in the water. Reduction of clarity in the water can inhibit plant growth, and the suspended solids in the water can potentially affect the ability of aquatic organisms to absorb or attain oxygen. pH measures how acidic or basic the water is. pH also determines the amount of nutritive substances that can be dissolved in the oxygen for use by aquatic life. Water that is too far from neutral is also likely to have chemical pollutants that change the pH. Most organisms can survive in the pH range of 6.5 to 8.5. Dissolved oxygen is crucial to the survival of aquatic life, as animals in the water need oxygen to survive. Chemicals and pollutants can affect the saturated oxygen levels, and other physical components of the stream can also affect dissolved oxygen levels. For instance, the faster the flow, the higher the DO, or dissolved oxygen. The next two tests are generally linked to overfertilization and runoff. Phosphates and nitrates are naturally occurring fertilizers in both water and soil, but in most cases, very little is needed for average plant growth. Overfertilization caused by nutrient pollution, however, can result in algal blooms, which eventually lead to eutrophication. Eutrophication is essentially where the water body has been overfed, and then the degradation of those algal blooms eventually drastically deplete oxygen levels in the water bodies. These tests can vary over time. So while chemical monitoring is important, it is not the only type of observation needed in a thorough stream study.
A couple of things we want to find when we're looking at our creek here is this nice amount of shade that we have around here. That helps keep the temperature of the water a little bit lower. We also are going to look at the flow of the water. If this were still water, it's not going to flush out as quickly as if it's moving. This moving water is flowing over this rocky substrate or bottom we have here in our creek, and this is a good indication that we'll probably find a lot of macroinvertebrates in and around here. This water flowing over these small riffles or small rocks is going to increase the amount of oxygen that's getting dissolved into the system. We're going to take our 1 meter square net now and anchor it down. Now I'm going to start to dance or shuffle to get little critters flowing onto this net. As I'm doing this, I want you to notice how clear the water is behind me relative to where I'm shuffling and over that way. This again is that turbidity, that measure of water clarity. You can see to the bottom of the creek there. Right here you can barely see my toes. If we look at places like Jamestown, for instance, and how that water quality changes over the years, in 1607, people like John Smith wrote that you could see to the bottom of the James River at 40 feet. Today, you can barely see your feet in those areas. Our sample has netted a good variety of aquatic insects. Let's take a closer look at a few. Remember when I said that our aquatic insects, our macroinvertebrates, are an indicator species of the health of the watershed? The two snails I have here might help illustrate why. This larger snail is a lung snail, and the tiny little guy right next to him is a gilled snail. As you might expect, the gilled snail takes in oxygen through its gills. Impairment or pollution present in the water can greatly reduce their number or kill them. The lung snail here will actually take in water by grabbing a bubble of air and breathing off of it like a scuba diver. Because of that adaptation, this lung snail can live in any quality of water. Here's another fun find. This fellow right here is not a worm or a maggot or a leech.
This is a larval form of a mosquito hunter, also known as a crane fly. We put our sample in an ice cube tray like this because the white contrasts nicely against the insect or aquatic insect, and we can better identify it. So if I see something squirming, it might be an aquatic worm, or it might just be a black fly larva like I have here. Now this guy is going to squirm around just like a worm will, but I can notice that one end of him is a little bit bigger than the other. That's an indication that this is a black fly larva. We also have a few other larval insects in here. This one and this one are larval dragonfly, and this one is actually an adult mayfly. Insects appeared first on land and then later adapted to aquatic environments. My bug volunteer, Zach, here is going to model a few of those key adaptations. When gathering food, caddisfly will filter their food, like our net here. Our fierce dragonfly predators will use pinching mouth parts. For stability in a fast-moving creek, black fly will anchor themselves to a rock using silk, much like a spider's silk. In acquiring oxygen, mayfly and gill snails will use gills, much like our feathers are showing here. And for predator protection, it helps to have excellent eyesight and, like our crayfish, a good sturdy exoskeleton. Or, like most of our aquatic insects in our creek, a good bit of camouflage. Like the historic cultures represented here at the Frontier Culture Museum, we too depend on water for life. A rich and dynamic watershed can be an economic engine in our community, and they're a tonic to the body and soul. We hope you're encouraged to explore your watershed, and we look forward to your visit to ours.